Recording. Let's go. Good afternoon, everybody. My name is Gabriel Palacios, and I'm going to present to you the high voltage design and evaluation of beam filters for the CEBAF200 kilo electron volt injector upgrade. This is a work we developed at Jefferson Lab's Injector group with all these awesome people. At Thomas Jefferson National Accelerator Facility, an upcoming experiment called the MOLLER experiment requires us to increase the injector energy from 130 kilo electron volts to 200 kilo electron volts. At Jefferson Lab, at the main accelerator at Jefferson Lab, we produce the electron beam using a photoelectron gun, or a photogun for short, that produces longitudinally polarized electron beam. We have to have precise knowledge and control of the orientation of the spin as we deliver the beam to the experimental holes, as you can see depicted here in this little cartoon. And we do so by using a device called a beam filter spin rotator in combination with the photoelectron gun. So the way the beam filter spin rotator works is that we have to produce independent, mutually orthogonal electric and magnetic fields, as you can see in this little red box on the right side. And the fields have to be inherent perpendicular with the velocity vector of the electrons that traverse the device longitudinally. The rotation of the spin, as you can see depicted here in this little cartoon representation, is described using the Thomas-Barkman-Michel-Telegdi equation, which is equation number 1. And we use it in combination with another equation that is referred to as the Wien condition that ensures that we don't change the trajectory of the electrons as they traverse the device. We use these two equations in combination to calculate the operational parameters of our device as we are trying to upgrade its capabilities to make it compatible with the 200 kilo electron volt energy of the beam. As part of my thesis work, I was in charge of the three-dimensional modeling and simulations of electrostatic simulations of the device, which is what I'm going to talk about. And there was also a part of modeling and simulations for the magnetic design that was carried out by another member of our team, but we're also going to talk about it. And of course, we use the electrostatic simulation results in order to qualify the modifications in the virtual world, because it's easier and cheaper. And yes, it allows us to do a lot of things and to evaluate our three-dimensional models too, in order to make sure that they are representing the actual device in a proper way. And yeah, we're going to talk about these results and how we use them to actually go and fabricate the necessary parts that we needed to upgrade our device, other parts we had to acquire and work with the vendors and all that good stuff. We're going to talk about how the assembly and high voltage evaluation went. Spoiler alert, it went really good. The device ended up behaving in a desirable way, so much so that it just recently passed its last tests to be installed at CEBAF, which is the main accelerator at Jefferson Lab. So we are very happy and humbled, and we want to talk about it. So please come to our booth, and I'll be more than happy to discuss these results in greater detail with you. All right, so I guess I'll see you there. See you around. Those are my references. How do this recording? Whoop. Oh, there you go.